All right, hello and welcome to our Wednesday edition of Chem 400 lecture. You may notice that we are light. We're missing a daily mixtape today, and for that I apologize. I had a morning of baby's doctor's appointment, so I only just was able to get him home, get him down for a nap, jump on and start streaming. So I will have a mixtape for you. I'll have it for lab, and then I'll go back and add it to the description. So for like the three of you who care to look it up, I will have that come in. It'll just be dropping a little later today than it normally does. I don't have any announcements. I haven't been able to look at any emails this morning. So if you have questions or are waiting for a reply, that'll be coming. But again, it's kind of been backloaded on the latter half of today because my wife's at work. And like I said, I had a morning of 2-year-old doctor appointments. So with that being said, I'm sure the inane details of my life are infinitely interesting. But let's go ahead and talk about some chemistry. So we left off on Monday talking about nomenclature, right? We are right in the thick of naming ionic compounds. And there we go. Complete that D with some green. So we're in the middle of naming ionic compounds, right? And we said that when you're given a chemical formula, naming the ionic compound is fairly straightforward, right? It's just cation name followed by anion name. But when we're given a name like potassium fluoride, that this is a little trickier, right? Because one of the beautiful things about naming ionic compounds is you don't have to worry about specifying how many of each ion are present. You just say cation name, anion name. It's also, it's a downside because we don't know by looking at it if potassium fluoride is KF, K2F, KF2, K2F3, right? We just don't know because the name does not explicitly state the number of ions present. And there's a way to determine this, and that is going to be the focus of our lecture today. So as we look at an ionic compound name, we need to be able to determine the chemical formula, right? And so there's a few guiding principles when it comes to taking a name and writing a chemical formula for ionic compounds that you should know and apply. The first is let's get back to black. All ionic compounds all ionic compounds are net neutral. Right, that is the first principle. Now, net neutral, what does that mean? Net neutral means that the total cationic charge equals the total anionic charge. All right. And you'll remember that cations are positive and anions are negative. So whatever the total amount of positive charge is, in an ionic compound, you'll have an equal and opposite amount of anionic charge. If you have a total positive charge of +2, then you have to have a total negative charge of -2. All right, so that's the first thing. All ionic compounds are net neutral. So it's our job to make sure that the amount of positive charge is the same as the amount of negative charge. All right. The second principle that you will want to use and keep in mind is this: all main group elements in ionic compounds, or I should say, all main group elements will gain or lose electrons so that they have the same electron count as their nearest noble gas. All right. Now here, this is the principle that we're going to use to determine the individual charge of your anion and cation in an ionic compound. All right. The fact that all main group elements want to have the same electron count as their nearest noble gas. Let's dig into this for a little bit. All right. Let me grab our periodic table. So the noble gases are right here. All right, they are the last column on the periodic table, as we talked about in lecture, I think a couple lectures ago, or maybe last lecture. So these are noble gases. Right there on the end. They're easy to find. And your noble gases are super stable. All right. They're actually the last set, the last group of elements to be discovered in nature, because they're inert. They don't react with anything. They're super stable. All right. They're like blissed out. They're zenned out. They just tend to not react with anything. And because they're stable, the rest of the main group elements spend their lives trying to achieve enlightenment, right? Trying to achieve the same stability that the noble gases have. The stability for the noble gases, and we'll spend some time later in the semester talking about this, derives from their electron count. All right. And so the main group elements will spend their lives trying to either gain or lose electrons, so they have the same number of electrons as the noble gases. All right. As their nearest noble gas. Okay. Let's see. Oh. Good to see you, Eric. Thanks for popping in. All right, so we're going to focus on the noble gases here as a way to determine the charges that our main group elements will develop. So let's just do a few examples so you can see what I mean. Let's look at. I'm going to move my periodic table. Let's do a couple problems. Let's do a couple examples, and let's determine the ionic charge for a few elements. determine the ionic charge for let's start with oxygen. All right, what kind of charge will oxygen develop? Well, the first thing that you got to do is you have to find oxygen on the periodic table. It's right here. All right, and then you look at oxygen, ask yourself how many electrons, how many protons does it have? Well, oxygen is the 8th element, so it will have 8 protons and 8 electrons. That's the element oxygen. Next, you need to find its nearest noble gas, which will be neon. Neon is the noble gas that's closest to oxygen. Now, neon has 10 protons and 10 electrons. All right? 10 protons, 10 electrons. So when oxygen becomes an ion, it's going to become an ion because it wants to have the same number of electrons as neon. It's going to change its electron count. It's going to gain electrons in the quest to become as stable as neon. But by doing so, it's going to throw its atomic neutral charge out of whack. Oxygen, though it can gain 2 electrons, will always have 8 protons, because that's what makes it oxygen. The proton count will never change. So when oxygen gains 2 electrons, it will develop a charge, a net charge of -2. All right? It develops a net charge of -2 because you have 10 negative particles, 8 positive particles. When you add those together, there are 2 negatives left over. So the ionic charge for oxygen is -2. All right, let's do another example. Let's determine the ionic charge for let's do magnesium, Mg. All right, first step, we got to find magnesium. It's right here. Magnesium has 12 protons and 12 electrons. All right. Magnesium's nearest noble gas is also neon, just like oxygen. All right, and neon, as we know, has 10 protons and 10 electrons. Now, magnesium, when it becomes an ion, it becomes an ion because it wants to be as stable as neon. Now, magnesium can't change its proton count because that's what makes it magnesium, but it can lose electrons so that it has the same electron count as its nearest noble gas. The charge here, after it's lost 2 electrons, magnesium has 12 positive charges in its nucleus, but now only has 10 negative charges orbiting the nucleus. So it will have a net charge of +2. So magnesium cations have a charge of +2. All right. So you're going to want to keep, when you're doing this, you're going to want to, especially at the beginning, keep the periodic table handy for reference, because this is the key to determining the charges that will be developed by your main group elements. All right. All the elements in the main group want to be like their nearest noble gas. And so this is what we're going to reference to determine the individual charges for atoms. All right. Now let's go ahead and apply this to our, the question that I posed. What is the chemical formula for potassium fluoride? All right, let's return now. Oops, not fluoride. Potassium fluoride. All right. So first things first, we need to find potassium on the periodic table. All right, and potassium is right here. It's number 19. All right, its nearest noble gas is 18, argon. So potassium starts with 19 electrons. It needs to lose 1 electron. So as an ion, potassium is going to pick up a charge of +1 because it's lost 1 negative charge. All right. Now let's take a look at fluorine. All right, where does fluorine land on the periodic table? All right, fluorine is number 9. Its nearest noble gas is neon, number 10. So fluorine needs to gain 1 electron, will gain 1 electron when it becomes an ion. And if you've gained 1 negative charge, that means you will have a net charge of -1. So this is the potassium cation and the fluoride anion. And once you've determined the individual charges of your ions, now you move to that first principle where our total net charge is 0, right, for every ionic compound. And since we have a +1 cation with a charge of +1, matched with an anion that has a charge of -1, this tells us that we are dealing with a 1-to-1 ratio, cation to anion. So potassium fluoride will have a, well, that's the ugliest K I've ever drawn. Potassium fluoride will have a chemical formula of KF. All right? So that is how you determine the chemical formula of an ionic compound based on the name. Let's do a few more examples. All right, let's look at, well, how about we do calcium bromide. All right, what is the chemical formula for calcium bromide? First, let's look at our cation, right? Calcium has 20 electrons. Its nearest noble gas is argon with 18. So calcium has 20. It wants to have 18 electrons. It's going to lose 2 electrons. So it is going to develop a charge. If it lost 2 negative particles, it's going to pick up a charge of +2. All right. Now let's look at our anion bromide. Bromide is number 35. Its nearest noble gas, krypton, has 36. So bromine, to become an anion, needs to gain 1 electron. All right, it's gaining 1 electron, so it will develop a charge of -1. All right. Now, when you compare these two charges, you got to ask yourself, how many bromides do you need to balance with calcium? Because we know overall we have to have a charge of 0. If we have 1 and 1, +2 minus 1 is still going to be +1. We need it to be net 0, right? We need all of our charges to cancel. So to do that, because each calcium ion has a +2 charge, we need to bring 2 of our negatively charged calcium, or our negatively charged bromide anions, to balance with it. All right, so calcium bromide is CaBr2. All right. Okay. So let's do another example. At least one more, maybe a couple more. How about we do Okay, yeah, let's go ahead and write the chemical formula for barium oxide. All right, so first and foremost, barium, our cation, we got to locate it. It's right here, number 56. Its nearest noble gas is xenon, number 54. So here, barium has to lose 2 electrons, which will give it a charge of positive 2. We've lost 2 negative particles. Oxygen is located right here, number 8. Nearest noble gas is neon, number 10. So here oxygen needs to gain 2 electrons. So oxygen will develop a charge of negative 2. Again, we see here we have a positive 2 to a negative 2. Our ratio here is 1 to 1. So barium oxide is simply BaO, and that's it. Because 1 barium has the equal and opposite charge of 1 oxygen. All right, let's do one final example before moving on to the next thing. Let's go ahead and do let's do aluminum sulfide. All right, this one's tricky on a couple counts. First, the cation is probably the most devious cation I could throw at you. All right, if aluminum was a character from the FX series, What We Do in the Shadows, aluminum would easily be Simon the Devious. All right, and here's why. If you look at aluminum on the periodic table, you might think that its nearest noble gas is argon. All right, but when you look at the electron counts, aluminum has 13 electrons. Argon has 18 electrons. But neon has 10. So aluminum is actually closer to neon, not argon, even though they're not on the same row. All right? So be aware of that. Aluminum's what determines your nearest noble gas is not the row necessarily, it's the electron count. And aluminum is a lot closer to neon, electron count wise, than it is to argon. So that's one reason why aluminum is Simon the Devious. Aluminum is, so aluminum needs to lose 3 electrons to become like its nearest noble gas. And if you're losing 3 negative particles, the resulting cation will have a charge of positive 3. All right. Looking at sulfide. Sulfide is the anion based on the element sulfur. So let's locate that. Sulfur has 16 electrons. Its nearest noble gas is argon, which has 18. So sulfur needs to gain 2 electrons to become like argon. So it will pick up a charge of negative 2. Now, we know that our net charge, our total charge for our ionic compound needs to be 0. It needs to be net neutral. That means our positives need to equal our negatives. But 3 and 2 don't go into each other. At least evenly. All right, so what do we do here? All right, there's a little trick. Whenever you have two charges that don't go into each other evenly, there's a trick on how to handle it. All right. We know we're going to have aluminum and sulfur in this compound. Take the number for your negative charge, make that the subscript for your cation. Then take the number for your cationic charge and make that the subscript of your anion, and you will come out golden every time. All right. The equation, the chemical formula for aluminum sulfide is Al2S3. Now, you may be wondering, you're like, okay, Josh, cool, nifty trick, but why does this work? All right, here's why it works. You have Murat, that is an excellent question. Stay on the line. I'll get to that in 1 second. First, I want to illustrate why this works. So here you have two aluminum cations, right? That means you have 2 times the charge on aluminum, which is +3. So you have a total positive charge of 6. In addition, you have 3 sulfur ions, right? So you've got 3, and sulfur, as we know, has a charge of -2. 3 times -2 is -6. So this is the reason why this trick works, because it makes your total, when you swap, when you multiply each one by the other's charge, it gives you the same total positive and total negative charge. And so you want to use this when one charge does not go into the other evenly. All right, now, Murat brings up an excellent question. What happens if you have an element with 14 electrons, which would be silicon? All right, silicon, which is located right here, everybody's favorite element. You'll notice that silicon has 14 electrons, and this is, so the question is the nearest noble gas argon or neon? Well, neon has 10, so silicon's 4 away. Argon has 18, so it's also 4 away. Which one does it roll with? All right. And you bring up a very interesting row in the periodic table. So this silicon and okay, so actually, hang on. So here's a super important thing. Silicon and carbon. So this row in the periodic table, the one we're talking about right here, it's column 1, 2, 3, 4. It's the 4th column in the main group. Silicon and carbon tend to form covalent bonds. Covalent, not ionic. And so you don't really see silicon or carbon, forming ionic compounds like this. Because they're right smack dab in the middle. They could just as easily form a -4 charge or a +4 charge, but they don't really like to form either of them. All right, so with silicon and carbon, don't worry about them. I'm not going to throw it in there and ask you to determine a charge. Because, again, they prefer to form covalent compounds. They don't really do the ionic thing. Now, for the rest of this column, So for germanium, tin, which is SN, lead, which is PB, and Florida, which is FL. I actually don't know what that one is. That one was named after my time. Back in my day, this bottom row on the periodic table were all like U, U, M, U, U, S. All these, they hadn't been named yet. Now they have, and so I don't know FL, so I'm just going to call it Florida Man. These for elements behave. Behave like transition metals. Which you'll notice that we haven't yet learned to name any compound that has a transition metal. And so, which is actually where we're headed next. So you'll learn how to handle germanium, tin, lead, and FL in just a few minutes. And you don't need to worry about silicon or carbon showing up in ionic compounds because I won't go there. Usually when they do, especially carbon, it shows up as a -4 if it has to swing one way or another, but they really don't like to. So I will not be testing you on those on silicon or carbon in ionic compounds for the lecture section. Germanium, tin, lead, and FL. We'll be dealing with those as we learn the transition metals next. Let's see. Totally solid question. Okay. Now let's talk about the transition metals. All right, let's talk about transition metals. The D block, right, or the transition metals are all the ones in here. And they march to the beat of their own drummer, all right? We've been dealing exclusively with main group ions, and those ions are all very predictable, right? They all want to have the same electron configuration as their nearest noble gas. And so by looking at the position relative to the position of their nearest noble gas, you can determine their ionic charge. The transition metals are not that predictable. They don't follow that trend, that behavior pattern at all. You have in the transition block some of the most diverse and interesting reactivity found in chemistry, period. I think the transition block is amazing. It's awesome. But with that diversity of reactivity and properties comes complexity, right? We can't predict them. The predicting of their behaviors and their charges are not as straightforward as it is for the main group. And now this, you may be hearing me talk and say all these things, and you may be going like, oh no, this is where things get bad. But in a way, because the transition metals are more complex, it makes it easier for you in this sense. When you are naming an ionic compound that has a transition metal, the charge of the transition metal is always explicitly stated in its name. Because there's no way to repeatably, reliably predict the transition metals' charges based on their position on the periodic table, we have to explicitly state the charge of the transition metal in the name when it's given. This will make your job easier and harder. It'll make it easier if you're given the name of a transition metal or a compound containing a transition metal, because the charge will be right there in a parentheses. It'll make it harder because if you're given a formula and you've got to determine a name, you must also figure out what its charge is, all right? So one way it's a little faster, the other way it's a little slower. It works out to be pretty much the same. All right, so what am I talking about? How is the charge explicitly stated? Well, it'll be explicitly stated like this. Let's do an example. Let's write the chemical formula for chromium 3 chloride. All right, just so you know, the way that you write this out, or it's not write it out, that's how you write it out. The way that you state this, if you're reading this, you heard me say that this is chromium 3 chloride. That's how you say the name of this compound, chromium 3 chloride. And the Roman numeral here, that 3 is the charge of the transition metal. All right, that is the charge of chromium right there. So we know that chromium has a charge of positive 3. What about chloride? Well, chlorine has 17 electrons. It wants to be like argon, which has 18. So chlorine will develop a charge of -1. We've got a positive 3 cation, a -1 anion, and we're going to need to bring 3 chlorides to balance the charge of chromium. So chromium 3 chloride, interestingly enough, will be CrCl3. All right, that is the chemical formula for chromium 3 chloride. Again, I want to explicitly state that this 3 is charge, not the number of atoms. You may hear the name chromium 3 chloride and think, oh, that means we got 3 chromiums. It doesn't. It means the charge on chromium is 3, which, as things work out, means that we need 3 chlorides in our chemical formula for the molecule to be net neutral. All right. Let's do a few more examples. Let's get some reps in with our transition metals. So again, we are going to determine the chemical formula for let's do another one. Let's do tin 4 oxide. All right, tin 4 oxide. Well, first we have tin 4. Now, tin has the chemical symbol SN. It's if you're like, why tin doesn't start with an S? It doesn't, but stannous does, which is tin's Latin name, and that also means that it's a pun because Stannis Baratheon is a little tin soldier. So tin has a charge of positive 4 in this compound. Oxide, well, that's an anion based on oxygen, which normally has 8 electrons, but as an anion, it has to gain 2 to have the same number of electrons as its nearest noble gas. So oxide has a charge of -2. And now to balance these, 2 goes into 4 twice, right? So we need 2 oxide anions to balance with the total charge of tin in this molecule. So tin 4 oxide will be SnO2. All right. Let's do a few more. Let's determine the chemical formula for I don't know. Let's do polonium. Let's do polonium 3. I don't know. Let's do polonium 3 fluoride. All right. So polonium 3 fluoride. Well, we know the charge of polonium because we're told, right? It's got a charge of +3. Fluorine, let's figure out our anionic charge. It has 9 electrons. It wants to gain 1 to be like neon. So it'll have a charge of -1. So we're going to need 3 fluorides to balance with our charge for our cation. Now, if you've noticed, I want to highlight this. So I just did an example with polonium. I just did an example with tin. You may be looking at those and going, well, wait a minute. Like, those look like they're in the main group. And I'll know when I see a parentheses next to it, like, oh, this works like a transition metal. But you may be wondering, how do we know? Like, because those look like main group elements. So you may be thinking, like, I would have just assumed that they would have behaved like main group elements. And here's how you know. Remember the railroad tracks that kind of start between boron and aluminum and go down, that divide metals from nonmetals? Right? Whoops. This is a big thing you want to keep in mind. All right. The main group metals and metalloids below this line behave like transition metals. All right, and again, we will get into the reason why that is a little bit later in the semester. But for now, as far as naming goes, whoa, let's flip that back. These behave like transition metals. All right, we'll talk about the why in the future, but for now, just roll with that. So If you're using a periodic table that doesn't have that line, I would just sketch it in there, because all of these metals in transition, or all of these main group metals beneath this line, and all these guys down in here, and the metalloids, these guys will behave like transition metals. The rest of the main group metals don't, but these guys do. All right. Okay, we've gotten some reps in taking a name and determining the chemical formula. Let's practice moving in reverse. Let's practice taking a chemical formula and determining a name. So determine the name for determine the name for well, let's do this. All right. Now, whenever you're naming, we know automatically that it's going to be anion, cation name plus anion name, right? Our anion's name is oxide. Our cation's name is copper. And you'll notice that copper is a transition metal. So whenever I'm writing out a name that has a transition metal, I write it out, copper, and then I open and close a parentheses to remind myself that I need to go back and figure out what the charge is, because I need to put the charge of that cation in Roman numerals inside a parentheses. So this will be copper blank oxide. It's up to us to figure out what that blank is, all right? What goes in that blank. Now, the way you figure that out is, well, I'm about to show you. We know that if you add up the charge of both copper atoms plus the charge on oxygen, that these have to add to 0, all right? Because this is what it means to be net neutral. All right, that's the definition of net neutral. All of the cationic charges plus all the anionic charges add to 0, all right? Now, we don't know the charge on copper, but we do know the charge on oxygen, right? Oxygen will want to pick up 2 electrons to become like neon. So we know that 2 times the charge on copper plus the charge on oxygen, which is -2, has to add to 0. That means that 2 times the charge on copper is equal to +2. And if you divide both sides by 2 here, you get a charge on copper of +1. That means that the name of this compound is copper 1 oxide. Again, not because there's only one copper atom, but because the charge on each copper cation in this compound is +1. All right, let's do another example. Let's determine the name for oh, I know. How about, whoops. Let's determine the name for FeO2. All right, well, iron is right here. It's a transition metal. Oxygen is up here. So I know that this name is going to be iron blank, I don't know what the charge is, but iron something oxide. All right, let's now determine what that charge is. We know that the charge on iron plus 2 times the charge on oxygen will have to add to 0. We can look at the periodic table to determine that oxygen's charge as oxide, as the oxide anion, will be -2. So we can punch that into the equation and now solve. We know that iron minus 4 equals 0. So iron in this compound must have a charge of +4. So this will be iron 4 oxide. BMP, that is a great question. So you only use prefixes, like di, tri, etc. when naming covalent compounds. Oops. All right, so BMP Draws brings up a great question. You never use prefixes. So you may look at this and like, this looks like maybe iron dioxide. You never use prefixes when you're naming ionic compounds. You'll only use those when you're naming covalent compounds. So those will circle back around once we finish our section on ionic nomenclature. We'll move to covalent stuff, but as long as you're dealing with cations and anions, our focus is charges, not prefixes. So totally. All right, so iron 4 oxide is the name of this compound. Let's do another example. Nope. Oh, wait. I'm giving you the formula. You're supposed to determine the name. Let's do this. Let's name this guy. All right, again, we've got the same players here. We're dealing with iron, and we're dealing with oxide. So the name here will be iron blank oxide. Again, I'm putting that parentheses in there to remind myself I still have more work to do. Because if I just wrote iron oxide, it would be wrong. I'd get a 0. Now we need to find the charge on iron. Well, we don't know iron, but, whoa, something happened to my pen. There we go. But we do know the charge for oxygen, or oxide, I should say, is -2. And this will add to 0. So if the charge on iron -2 is 0, that means the charge on iron must be +2. So this would be iron 2 oxide. All right, let's do one more example. Let's name this guy. All right, again, the name will be iron something oxide, and we need to determine what goes in that parentheses. Here we have 2 iron cations, and 3 oxide anions. So the charge of our cations plus the charge of our anions sums to 0, because that's what it means to be net neutral. And so 2 iron plus the charge of 3 oxide anions, which each have a charge of -2, have to sum to 0. That means 2 times iron minus 6 equals 0, which means that 2 times the charge on iron equals +6. In our last step, we divide both sides of this equation by 2 to find that our iron cations each have a charge of +3. So this is iron 3 oxide. Now, if you look at the last 3 examples we did, right? We did FeO2, FeO, and Fe2O3. The reason why we can't just call our transition metal compounds iron oxide is because these 3 compounds have 3 different molecular formula. They have different atom counts. They even have different empirical formula. And so we need to include the cationic charge to differentiate one from another. All right, it is the blessing and curse of transition metals. They're very diverse, but because they're so diverse, we have to explicitly label which cation we're dealing with, because there are a lot of different types of iron out there, which is also an interesting thought. All right. So that is our introduction to naming ionic compounds that contain transition metals. Before we leave our transition metals, there's one last piece of ionic compounds that we have to discuss. One last piece of ionic nomenclature we have to go over. But before we leave our transition metals, I do need to say one more thing. You should be aware that there are some transition metals I'm going to use TM, transition metal, with an abbreviation there. There are some transition metals that always have the same charge. All right. There are certain transition metals out there that will always have the same charge, no matter what. And I don't require you to have these memorized, but I want to make sure that you're aware of them. Because, for example, in some resources you may read, in the textbook or the lab manual or what have you, they may not explicitly state the charge of the transition metal. And so you may be going, well, what's up? If they don't, it's because that particular transition metal always has the same charge. And so it's understood and used as shorthand in the community that when you say, for example, silver will always have a charge of +1. All right. So you don't always see silver with a Roman numeral 1 written in parentheses because it's understood silver's always +1. Zinc is another one. Zinc is always +2. Cadmium is another one. Also +2. Scandium Sc is a +3. Same with yttrium. Also +3. Lanthanum also. will always have a charge of positive 3. Now, you do not have to memorize these. You don't have to have them memorized. But I want you to be aware that they exist. So if you are doing a lab write-up and something uses silver chloride, you're like, well, how do I know the charge on silver? Because silver is a transition metal element. I have no way of knowing what it is. You'll remember this moment and you'll be like, oh, is that one of the ones that always has the same charge? You'll look it up. Turns out it is. And you'll know that silver is +1. You can determine chlorine is -1. So silver chloride would just be AgCl. Cool? All right. So with that out of the way, you can now handle any naming any ionic compound with that has a transition metal in it. There's one last thing to talk about, and then we will have completed all of ionic nomenclature. And that last topic is the topic of polyatomic ions. Ionis. There's only one I in ions. All right. Polyatomic ions. Polyatomic ions are exactly what they sound like. They are ions that are made up of more than one atom. Eric, the answer to that question is in the syllabus, but I also don't mind answering now. No assignments, quizzes, or tests are dropped. So everything counts, just like life. All right. So let's see. All right, polyatomic ions. They are exactly what they sound like. They're an ion that's made up of more than one atom. So they are a group of atoms that together have a larger aggregate charge. All right. Now, when I'm teaching this class in person, I have my class, I tell them to memorize the polyatomic ions. As with everything in this class, you technically do not need to memorize them because it's open everything, so you can always look them up. But I still would recommend memorizing because there are going to be testing situations where time is a factor. And so if you are having to waste time looking these things up, that's time that you could be spending solving other problems. So I recommend memorizing them because it will help you in time and pressure testing scenarios. All right, now these polyatomic ions, you can find them in your textbook. I'm going to write them all out here because not everybody has the textbook yet, and so, or some people may have chosen not to buy the textbook, and so I want to make sure that everybody knows what to expect, what ions you're going to see show up in a testing format. All right, so here are the polyatomic ions you will be encountering on exams and quizzes. The first is ammonium. Actually, I'm going to scoop this over just a little bit. All right, ammonium is, oh, hang on. NH4 with a charge of positive 1. Next we have C2H3O2. This is acetate. Something to keep in mind, sometimes acetate is written like this, C3CO2 negative, or CH3COO negative. All of these forms of acetate are acceptable. All right. I'm going to stick to C2H3O2, but you might be reading other things and you're like, what's that weird thing? It's just an acetate. Next, we have a cheery one, cyanide, which is Cn with a negative charge. We have hypochlorite, which is ClO, charge negative 1. We have chlorite, ClO2, the charge of negative 1. We have chlorate, ClO3 with a negative 1 charge. And we have perchlorate, which is ClO4 with a charge of negative 1. We have MnO4 with a charge of negative 1. This is permanganate. Or actually, let's do this in. I can draw a better line. Okay. I'm like, this is not a good time for OCD to go out of control. Let's see, that's permanganate. We have hydroxide. Oh. Which is OH minus. We have nitrates, NO3 with a negative 1 charge. We have nitrite, which is NO2 with a negative 1 charge. We have peroxide, which is O2 with a negative charge. We have carbonate, which is CO3 with a negative 2 charge. We have bicarbonate. Sometimes this is called hydrogen carbonate, which is HCO3 with a negative 1 charge. We have sulfate, SO4 with a negative 2. We have sulfite, SO3 with a negative 2 charge. Let's see, how are we doing? Here we go. We have bisulfate, which is HSO4 with a negative 1. This is also called hydrogen sulfate sometimes. Bisulfates. We have bisulfites, which is HSO3 with a negative 1 charge. Let's see, we have CrO4 with a negative 2 charge. This is called chromate. We have Cr2O7 with a -2 charge. This is called dichromate. Finally, PO4, the -3 charge, is phosphate. You have HPO4 with a -2 charge. This is hydrogen phosphate. It's not biphosphate. This is called hydrogen phosphate, because you can also add a second one. You could do H2PO4 with a -1 charge, and this is dihydrogen phosphate. All right, these are the polyatomic ions that will be in heavy rotation this semester. Everybody you all made it through a pre-req course, so you have some experience with some of these ions, but I know, for example, I taught Chem 305 over the summer, and the number of polyatomic ions that we use in Chem 305 is very, very limited relative to the ones that you run in this class. So this is the list that I recommend memorizing. This is something that all of these will show up on exam 1. Every single last one of them. So you're going to need to be familiar with these. All right, so now that you've seen them, all right, and these are the ones that you want to be familiar with. These are the ones, again, that I recommend memorizing. Let's get some reps in using them to name ionic compounds. All right. So we'll start with write the chemical formula for and so now let's write the chemical formula for sodium phosphate. And for this, we'll pull up our periodic table. Sodium is Na, is its elemental symbol. Sodium has 11 electrons. It wants to be like neon. So sodium will have a cationic charge of +1. Phosphate is a polyatomic ion. So we don't look to the periodic table. We just need to know that phosphate has a formula of PO4 and a charge of -3. All right, so because we have a -3 and a +1, we're going to need 3 sodiums to balance with phosphate. So here, our chemical formula will be Na3PO4. All right. Let's do another example. Let's do titanium 4 sulfate. All right, here's one that we don't need the periodic table at all for. Titanium is a transition metal, and in this compound, it has a charge of +4. Titanium is Ti. Sulfate, polyatomic ion. So we just need to know that sulfate has a formula of SO4 and a charge of -2. Now, 2 does go into 4 evenly, right? It'll take 2 sulfates to balance with 1 titanium. But here's the thing. You cannot write TiSO4 2. All right, this gets you a skull and crossbones because that literally means 42 oxygens. All right, I have no idea what compound has 42 oxygens, but I guarantee you it's not titanium 4 sulfate. Anytime you have multiple polyatomic ions, to show that, you need to place your polyatomic ion within a parentheses. So you open a parentheses, write SO4, close parentheses, and then subscript it appropriately. All right, so this is the chemical formula for titanium 4 sulfate. Anytime you have more than 1 polyatomic ions, you need to throw it in a parentheses. One quick note. Some students hear this and they think, oh, well, I'm just going to automatically throw any polyatomic ion in parentheses. But you shouldn't. The previous example, where we did a sodium phosphate, right? Sodium phosphate. This is correct. This is incorrect. All right? You never use a parentheses when you only have 1 polyatomic ion. Never. It's wrong. You always use it whenever you have more than 1 polyatomic ion. Okay? So don't just slap one on everything. Only use the parentheses when appropriate. All right? We're almost out of time, but let's do a problem in the reverse order. Let's name the following. Let's name tungsten. Oh, well, let me be careful here. Let's name this. All right, well, W is for tungsten, right? It's because there's a silent W. No, there's totally not a silent W in tungsten. But this will be tungsten something. And then the name of our anion here, it's a polyatomic ion, hydroxide. Tungsten something hydroxide. We need to determine what charge tungsten has. All right, and to do this, we know that the charge on tungsten plus 6 times the charge on hydroxide has to add to 0. Now, hydroxide, polyatomic ion, has a charge of -1. So we know that tungsten -6 equals 0. So that must mean that tungsten in this compound has a charge of +6. So this would be tungsten 6 hydroxide. All right. Now, before we go, I just remembered that there's 1 polyatomic ion I forgot to mention. which is bad because this is a polyatomic ion that you will absolutely get tested on. And I'm going to put it down here in a weird color. The polyatomic ion, oops, nope. Hg2, 2+. This is the polyatomic ion mercury 1. Now, if you're going, why is it mercury 1? Because there's 2 mercuries. Well, remember, what goes in parentheses is its charge, right? It's the charge that's in the parentheses. And if your total polyatomic ion has a charge of 2, and there are 2 mercury ions in that polyatomic ion, that means that each individual mercury has a charge of positive 1, all right? You will get tested on that business. So in a way, I'm glad I forgot it, because now it's highlighted in a special way that will offset it from, hopefully offset it from everything else in your memory. It's getting lightning bolts. You will see this on tests. All right. So with that, let's go ahead and I'm going to go ahead and close out lecture. Thanks everybody for coming tonight. We have office hours. There is no pre-programmed lab lecture, right? So again, it's just going to be whatever you guys want to talk about. I'll be hanging out 7 to 10. Come say hi or don't, at your leisure. Thanks for watching. See you to some of you tonight, and all of you on, well, not Monday morning, Monday afternoon. All right. I will catch you guys on the flip side.